Well, welcome. How's your day been going? Excellent. Sorry. My name is Adam Beehler, and my title here at the University of Utah is Lecture Demonstration Specialist. I haven't had anybody laugh before. That means I do demos. I'm a resource for all the classes in the Department of Physics and Astronomy. If an instructor would like help teaching a principle or a concept, would like to use equipment to do so, because they're not getting it, or they don't believe them, or see it really does work, or wake them up, or to help get the concept across, because not everybody gets it from formulas or reading the text, then I hook them up. And this area back here is all devoted for such demonstrations. And what are some topics in physics that you already know of? Just shout them out.
Gravity.
Electricity, gravity, fluids, magnetism. What was that?
Acceleration.
Acceleration and forces, motion. Yeah, now you're thinking. Good. Okay, we got your juices going. Heat, sound, light. Those are all physics. I sum physics up as the way things work. It explains why the seat keeps you up, why you're attracted to the ground, why you can see me, how you can hear me, how your heart can pump blood out. The physics are the laws and sometimes theories behind all this. Today I've chosen electricity as the theme. So these demonstrations, we'll try to get through as many as we can. I always have too much set up, but that's okay. I would like you to know if you have questions, please ask. This is for you. You might as well learn what you'd like to know instead of me just up here going like this. So, any initial questions? All right. Well, let's start with the first one. I'm going to start way at the basics with electricity. There are two types of charges in this world, and only two. Do you know what they are? Like, positive and negative is one answer. AC and DC was another. AC and DC is very close. AC is alternating current. It changes directions, which way it flows. And DC is direct current, only in one direction. What's flowing are the charges. And the two types of charges are positive and negative. Very good. Do you know what the source of those charges are? What makes them positive and negative? Electrons and ions. And the ions because they're the nucleus of an atom, and it's the protons. So ultimately, it's protons and electrons, which everything's made up of. So I'm going to start with these two ping pong balls and this hair, and I'm going to rub them. And every time I come off of the ball, charges separate. The hair prefers to give up electrons, and the plastic prefers to take them. All materials have an affinity or not, one way or another, for electrons. So these are both charged up negatively. And what can you tell about two negative charges? Yeah, they don't like each other. They repel. Yeah, even if you didn't know that they were negative, you would know they're the same charge because they repel. How would I get the charge off of them? Touch them? Now I can teach you about insulators and conductors, or review. Plastic, wait a moment. So I'm going to take rubber and separate it from the hair. It's going to become charged negatively. It likes electrons. I'm going to transfer them to this electroscope. They spread out because they don't like each other. And the ones that go on the needle, they don't like the ones on the mount, so they tip over. I'm going to take the metal rod and touch the top. What do you think will happen? Sparks. See? Yeah, that'd be fun. That's later. Okay. Oh, what will happen? The needle will move. Which way? You think it'll deflect more or less? More. Good scientists make predictions. They're called hypotheses. And a hypothesis is just it's an educated guess. Based on what you already know, you predict. I don't expect you to be right, and it's okay if hypotheses are wrong, but commit to something. It's more fun that way. All right. Then you do the experiment. Neutral, very good. The excess negative charges on there could flow through the metal and into ground. I gave it a path. So we call this a conductor. Conductors allow charges to flow across them. Let's do it again. What do you think will happen with a plastic rod? So it'll discharge. The excess charges can flow off. I also heard somebody say nothing. They won't flow off. Who thinks it'll blow up? Boring. So we call this an insulator. Charge was touching right here, so some charge came to it right here, but it's not allowed to move freely across the plastic, so that's an insulator. Good. Who thinks insulator? Conductor? Who doesn't know? Who doesn't care? Okay. I used to think wood was an insulator too, but I'm never going to trust my life to it because it's actually, it's not as good as a conductor as metal, but it does conduct electricity, especially if it's wet or newer wood, has more moisture in it. So it can act as a conductor. So the ping pong balls, when I touched them, only the charge where I touched it came off. It still had charge elsewhere. So I'd have to like touch the whole thing. You know, let's let charge from every surface try to get off. Then they're not as impressive. Okay, let's do this 2x4. Is this positive or negative? Neutral. What does neutral mean?
It means that the ions are equal to the number of neutrons.
Yeah, it doesn't mean it's not positive. It doesn't mean it's not negative, which are both true. I'd be more specific. It does have positives in it. It's made of protons and electrons, but they're balanced. It has no excess. So I'm going to charge up this rod. Remember, it becomes negative. I'm going to bring it near the 2x4 without touching it. What's happening? Think about it. This is negative. This has negatives in it. Do negatives like each other? No, same charges repel. And so the negatives in here kind of get pointed away from here. And the positives are pointed towards, attracted to it. So it's temporarily charged, if you will. We call that polarizing it or inducing a charge. Once I remove it, it goes back to normal. Maybe that. Now, I know you guys don't all have, you know, cat fur lying around and rubber rods. How about an oven bag and a pink flamingo? I want to see, who has a pink flamingo at home? See? So you can try different things. Almost everything has an affinity or not for electrons or not. So you can just try rubbing two things together, and I'm sure you'll separate charges. So let's try it now. Yep, still works. And you guys have done this before, whether you realize it or not. Raise your hand if you have ever, thanks, blown up a balloon and rubbed it on your hair. I don't think that was everybody. Thank you. That is the first question I always get asked. Are you gonna explode anything? No. Usually that's more chemistry. But all right. I chose this balloon because you'll see. Let me seal it off. Close the door. And I hope you know why it doesn't work. It's still neutral. let's separate some charges. Piece of cake. Now the door is doing the exact same thing as the 2x4. It's polarizing it, temporarily causing it to be charged. Let's see. That works. This balloon, I chose it because this isn't its original intent, is he's charged and stuck to the wall. It's more fun when you let the air out. Why is it sticking to the wall? It's charged. And that charge is more densely packed. Wow, science. I need a volunteer. Who'd like to get charged up? Let's see. Would you help? Come on now. Come on back here, pretty please. Back here. I'm going to ask you to stand here like this.
Should I remove my
No, it's safe. All right. You will not get shocked if you don't let go and don't get too close to touching anything. You trust me? You good?
Yeah.
All right. Even if it shocks you, it's safe and it just surprises you more than anything. It's not painful or anything. But you shouldn't get shocked if you don't touch anything and don't let go. Let's turn it on and talk about it. This is called a Van de Graaff generator, and I have it plugged in. All that's doing is rotating a motor. Just a second. What do you think that is? Your zipper, maybe?
Your coat?
Yeah. You want to take the coat off?
Sure.
You can let go now. And talk that to me. He's charged up. Thanks. I'll just keep it right here for you. We'll try this again.
Give him a handshake.
Are you set?
Yeah.
You good? All right. Let's see. Not as bad. The motor is driving a belt up and down. And that belt is coming off of the roller and it's separating. Charges. Long story short, the charges accumulate on the dome and him. It's the same charge. Same charges don't like each other, so they try to get as far away from each other as they can. Stand up and spread apart. Shake your head.
No.
Okay, I'll free you. Don't let go yet. Now you're safe. Give him a hand. And now your hair just went down, so you're safe. Thank you very much. Let's do this one real fast. If I pull tape off of a dispenser, I just separated this from the roll, just like the belt going around there, it comes off the roll. This is charged. Let's do it again, in case you missed it. Okay, this one's charged also. Do you think they're charged the same or opposite?
Same.
I would expect same because they came off the same way. So, let's say, I heard most people, well, if they're the same, what do you expect to happen? Well, let's find out if they attract or repel then. We'll know. Turn it around, still repels. So they're the same charge. You can, let me come around so you guys can see what I'm doing now. Just fold it over so I can get it off the table. Same with this one. stick them on each other's back, rip them off. Now they should be neutral, right? I'm taking the charge off. But what I'm going to, oh man, why do I, okay, there we go. Let's separate them. Now what? Yeah, so now they're opposite. One took more electrons than the other. Why does it want to stick to me? This one wants to stick to me. So does this one. It's polarizing me, inducing charge on me. But that's something fun you can do with just Scotch tape. And that's all this is doing, really. It's just doing it fast. The motor just keeps it going and charge builds up. So if you don't have a nice brave volunteer, you can use pie plates. Ready? Packing peanuts. This one goes a little more quickly, so I'll count to 3. Clean up. If we're lucky. All right, 1, 2, 3. All right. Now I want to teach you about lightning rods briefly. Why do we put a lightning rod on our house? I heard lots of good answers. I heard to attract lightning. I heard so if it strikes, it'll direct it to the ground instead of through your house. And I heard so it doesn't get struck in the first place. Let's find out which of any of those are correct. So this is charging up. This is ground. It's the water particles in the clouds rubbing, separating charges. It builds up, induces a charge in the ground. And if it gets big enough, a difference, whammo, spark. I know you can't all see it, but you can hear it. Let's see if I can help. So in between sparks, it's just trying to recharge itself. And that's lightning. Charge is flowing. Now, if I take a lightning rod, just a little sharp little point, I'll show you again when the lights are on, and get near my house, it's less likely to strike. Let's put it on the house. Whoa. What it's doing is allowing charge to dissipate away, and this does not get charged up as much. It can't store as much charge, so it's less likely to get struck in the first place. Now, these have to be that close before it would ever strike. That's the point of a lightning rod. It doesn't hurt that if it's going to strike, it can help try to redirect it, not through your appliances. But this is the main reason. Another way to show the same thing, let's put the hair on the Van de Graaff. And we'll turn it into you. So it charges up. Lightning rod. Recharges back up. Again, sharp points, which is what was happening to you when you first got on. I could hear that was some sharp edge allowing charge to dissipate off of you, and so you weren't charging up as much. That's why I was just having you remove like the zipper or something. Sharp edges allow it not to charge up as high. Okay. Let's do an interactive demo. I need volunteers, brave volunteers. We've been storing charges. We know what they are. We're starting to make them flow. Let's make a circuit. I need you guys to be the circuit. So if you're still willing, come down here, make a big circle, and hold pinkies with your neighbor if you'd like to. Come on down. All right, circle, scooch that way. And please let me in the center. Thank you. All right, thank you for volunteering. This is a capacitor. The dome of that Van de Graaff was a capacitor too. Something that can hold charge is a capacitor. A capacitor needs three things. Two conductors separated by an insulator. Here is a bottle of water inside with the bolt. That's the inner conductor. The outer conductor is the aluminum foil I wrapped around it. They can't touch each other because they're separated by the insulator, the plastic. This holds charge. That's all there is to a capacitor. It wants to get from one conductor to another, inside to outside. So if I'm touching the outside and I touch the top, now it has a path, and it will discharge. You guys are going to be the path, though. I need a switch. Deal. Can I hold your pinky? Well, I will in a moment. So I'm going to hold his pinky. I'm holding the outside. He's going to touch the bolt. The only way it can get to us is to go all the way around. And it will only move if it can see both sides of the capacitor, like a battery, at the same time. So if any of you let go, there's a break. It can't see, it will go. So you guys don't let go. And second, we want it to go through our circuit. We don't want leaks, like in any electrical component. So if you're touching the table, step forward a little, don't be leaning or whatever, and we'll call it good. All right. So when he's ready, you guys all holding? I'll ask him to touch the bolt on the top. You can sit down. Thank you. Thank you very much for volunteering. I can teach you a few things, though, from your observations. When did everybody yell?
After it went all the way through.
After it went all the way through. When it went through you, yeah, you yelled. Most everybody yelled. Yeah.
How did you, was the charge in the bottle?
Yeah, it's stored sandwiched between the conductors on the surface of the insulator.
How do you charge it like that?
Oh yeah, I hid that part from you. This is what I did. I held this up against here, turned it on for 5 seconds, turned it off. So that charged up, and some of it came into this like it went onto him. And then I just turned it off, and it was trapped until we gave it a path. That's what I did. So yes, you screamed when charge went through you. You all screamed at about the same time, though. For one thing, people think, and I did when I was a kid, that when you flip a switch, the charges are whizzing around at the speed of light. Not true. They're going fast, mind you, but not at the speed of light. This is what happens. You force a charge to move on one end, and watch what happens. As soon as you put it in, that one comes out. The wave travels fast. It doesn't take time. much time. When you flip a switch, oh, this one comes on, and then this one, and then this one, and then they're all like on like that. The individual charges aren't moving that fast, relatively speaking, but the wave travels. And so as soon as we close the switch, there's charge flowing in all of us at the same time in a series circuit like that. And everybody about yelled the same, roughly. You guys felt the same thing. Where's the switch? There he is. He did not feel any more than the last person, because as soon as you closed it, charge was flowing everywhere the same. So you all felt the same thing. Yes, you can do it with just one person. If I charged it up exactly the same and we discharged it through you, what do you expect to happen? Excellent. He would feel more because there would be less resistance. The less stuff it has to go through, the more charge it can push through. Let's do that one. We'll skip to this. This is a wire. Can you see it? It's really skinny. And anytime you force charges through something, there's resistance. Some have more than others. But the skinnier it gets, the harder it is to get through. And so this will heat up. That's how our light bulbs work. Incandescent light bulbs work that way. You send it through a really skinny wire, resistance, heats up, it starts to glow, and we have light. Let's do it. I'll turn off the lights because I think it looks cooler. You ready? Safety. Didn't want to kill myself, so I made sure it wasn't plugged in yet. Okay, now we're ready. Here it goes. Current flowing. Resistance heats up, and then it actually deteriorates. It reacts with the oxygen in the air. It gets so thin, it just breaks apart. That's like a fuse. Fuses do that. If it's rated at 10 amps, and more than 10 amps of current goes through it, that happens. Breaks the circuit, and now current can't flow, and hopefully in time to protect your valuable electronic device. So that's what happens when electricity is going through stuff. I'm going to charge this capacitor up. It's a lot scarier than that one. So I'm not going to ask for volunteers. I connect it to this power supply, set it to about 4,000 volts, turn it on, and now this is providing a charge like that did, and it's going into that capacitor like that one, and it's storing it. That should be long enough. Turn it off, disconnect it, and it wants to get from one conductor to the other, which are separated inside by insulators. So if I provide the path, all of that discharges at once. And so it packs quite a wallop. Let's do it again. How about with the lights off again? So plugged in, turn on the power supply, charging up, just like your rechargeable batteries. You can just keep charging them until the chemicals break down in the capacitor or the battery and they can't handle it anymore. Disconnect, and here we go. 1, 2, 3. There we go. Great question. Somebody asked, what happens if you leave the power supply plugged in? Then I get really mad at the PhD instructor that did that, because they should know better. This has a path across here, but it also sees a path through the power supply. And the power supply doesn't like that. And it fried it and ruined it. It was a sad day. All right. Let's do another high voltage. This guy. Yeah. Danger, danger. This is called a Jacob's ladder. And the two copper pipes, they're close together down here and far apart up there. This is called a transformer, and it takes the 120 volts out of the wall, steps it up to about 12,000 volts. So I love that. Whoa. I want you to know, this got charged up to roughly 200, 300,000 volts.
That's it now.
Yeah, it's how much current flows. The voltage is the push, what pushes the charge so it moves in the first place and makes current. But how much charge flows through you, current, is what kills. That has low current, safe. This has high current, dead. Okay, so let's do it. Again, double safety, so somebody doesn't come up and accidentally, unwillingly turn it on. So what's happening is there's a big potential difference or voltage from one side of the pipe to the other. A lot of charge on one side, not much on the other. A big difference in charge, positive versus negative. If it's big enough, like the Van de Graaff, it sparks. It can break down the air, ionize it, strip it of electrons, make it conductive. And a conductive path allows it to spark, lightning. What do you think it does to the air it goes through? And which way does hot air go? So it stays with the conductive air path and rises until it gets too far apart and it can't jump anymore. There's a hand over here.
Why do some go higher than others?
Wind currents. You see how it kind of gets blown around? Let's see, if I stop it, let the air kind of settle. This one a little higher. Just because the air is a little calmer. Because if hot air is rising, cold air is coming in the bottom and it's creating a convective air current through the tube. Every proper mad scientist needs one of these. But I guess you'd like to see something else too. Okay. We'll call that one good. So those signs you see, danger, high voltage. You should still be cautious because generally the more voltage there is, the more it can push, more charge it can push through something. And so generally when there's high voltage, there's high current. But it is the current that kills. However, I'm not going to dare touch that. It could burn the heck out of me, even if it won't kill me. I don't want to burn myself.
Once I was in this electricity class, and they had one of these in a smaller version, and it like pulled together as it got higher. Does it have like that pulling?
Yes, it can. There's something else going on. This one, because it's fixed. I have it so they can't move much. But the short answer is currents flows through one. When it sparks, flows up through the spark and down the other. And moving charges actually produce a magnetic field. And so each one has a magnetic field around them. And magnetic fields exert forces on moving charges. And so they pull together. And that's a great lead into my next demos. I want to make the connection to magnetism. So let's do that. This is a copper pipe. This is an aluminum slug. I'm going to drop it down the hollow inside, and you expect what to happen? Dun, da, da. Whoosh. Pretty dang exciting. Do it again. Whoosh. Good scientists do controls. We need to know what's going to normally happen so we have a baseline to compare to. Because now, yeah, about that. Okay. Strong magnet. Is copper magnetic? No. Is steel magnetic? Yes. Okay. So when I drop it down, it falls just like the aluminum slug. It's still falling. There we go. Again. I got this camera, so next one we'll watch you see what happens. Let's turn that one on. This is what's going on. Drop the magnet in. Again.
What is the clear part made of?
Oh, this is a magnetic view film. It has a nickel colloidally suspended in it. It's like iron filings, and they'll attract to the magnet, and they rotate, and the light changes. But if you bring it near it, you can get dark or bright spots. So watch again, if you can see from there. As it goes by, it's probably about here, and there. You can see it go by. As it affects the nickel in this film. Because you can't see inside without the camera or being up here. Now let's explain why that works. This is a coil of wire. This is a galvanometer. It measures if current's flowing through here. Is current flowing? No. This is a magnet. It has a magnetic field around it. Let's see that. Right, the on button's up front. There's a magnetic field. So it goes in that general shape. That field is going to go into this coil. Is current flowing? How about now?
Yes.
Now? Now?
Yes.
Now? What do you notice? Yeah. It only makes charges move around it when it feels a change in magnetic field. There's a magnetic field now. It's in it. It feels it, but no current flows. It must be changing. That's the key connection in my mind to between electricity and magnetism. Look, a generator. I'm making electricity. All generators work this way, pretty much. A magnet is moving with respect to a coil. The magnet is moving, or the coil is moving, or both. Doesn't matter. And it depends on which way you're moving it. But you need the magnetic field to be this to feel that change. So that's a magnet. It has a magnetic field. It's falling. So that feels a change in magnetic field. Is the copper a conductor or an insulator? Conductor. So the charge is already in there. Start moving. So the falling magnet induces charges to flow. Now, let's go back to this. These TVs are old anymore. They shoot electrons, charged particles, from the back to the front. They hit the screen, the phosphors glow, and you get your picture. But they're moving charges, right? So if I bring a magnetic field near moving charges, it deflects them. It exerts a force on them. And so magnetic fields exert forces on moving charges, deflects them. But changing magnetic fields cause charges to move. So follow me. Falling magnet, moving magnetic field. Makes charges move in the copper. Well, the magnet's magnetic field now exerts forces on those moving charges. It pushes on it. It pushes back. And that's why the magnet falls slowly. You can dampen out things with conductors and magnets when you move them around near them. That's the connection. You can make generators that way, like I was doing here. There's magnets and coils inside here. I just took out the battery, soldered up some wires, connected it to a light bulb, and now I'm going to run it backwards. Electricity. How many of you have one of these flashlights? They work exactly like the coil. Here's the magnet. Here's the coil. And it only shines light. The coil's connected to an LED. And there's only electricity flowing when the magnet's moving in and out of the coil. Just like that. Now this isn't very useful because you got to walk around like this, right? So what else do they do? flip the switch, and now instead of going through the light bulb, it goes to the capacitor and charges it up. It stores the charge until you're ready for it, flip the switch back, and now the capacitor goes through the light bulb. And there's your simple flashlight without needing batteries. The difference between a capacitor and a battery, yes. Simple answer, capacitor stores charge, can't create it. A battery, through chemical reactions, can allow charge to flow on its own when you connect up the two. Rechargeable batteries, somewhere in the middle. Seriously. Same idea. A magnet moves next to a coil. Loriana, do you remember I give you this on when we go camping? You know where you're at. I can hear you. And when she leaves it on, when she fell asleep, I didn't have to change the batteries. Okay. Let's see, we got about that much time. Time for the finale. Let me grab it. Called a Tesla coil, and it involves everything we've just discussed. I won't bore you with this time with all the grimy details again, but I will give you a 60-second primer here. Plug it in. 120 volts comes out of the wall. These things in the front are transformers like this. They, through coils, current goes through, creates a magnetic field. That changing magnetic field induces current in this coil, and you can change the voltage. It steps it up to about, these are 8,000. They are connected to this white that not all of you can see at the moment. That's a capacitor. It stores charge. Keeps storing until it's large enough, like the Van de Graaff, it can complete a circuit back here, a spark gap. Two electrodes, conductors not quite touching each other. So if big enough difference in charge, it will spark. Complete the circuit and dump all that capacitor's energy, remember the sparky one, in this coil, which then is not electrically connected to this coil. It is a charge in it. The charge builds up on here. It's another capacitor, this and ground. If it gets high enough, it sparks. And so it oscillates back and forth, slowly charges up. Bam-o! Of course, that happens about 1,000 times. Gets up to about 500,000 million volts. Let's do it. Oh, does anybody have a pacemaker? This does put out electromagnetic radiation that's safe, except to a pacemaker. We don't want to chance it. We would have them move to the back of the room, but that's good. Okay. behalf of the University of Utah and College of Sciences, thanks for coming. That was fun.